that methanol is manufactured by compressing a mixture of carbon monoxide and hydrogen to 3,000 times atmospheric pressure. Now the mixture is passed over zinc oxide that acts as what? A catalyst. Okay, so there are processes. The first process here is compressing, right? Getting a mixture of carbon monoxide and hydrogen. Getting, for example, a container, you know, a cylinder, and putting hydrogen inside there and carbon monoxide. Now, the element of compressing here means like either reducing the volume or putting as much of the two gases as possible, okay? That is so that they are in very much high concentration, or what? Very high number of moles. So yes, after compressing it that much or reducing the volume that much, it is then made to pass over what? Over zinc oxide, which is a catalyst at this temperature, what? 300 degrees Celsius. Now the chemical equation for the whole process is right here. They've indicated it for you, and delta H is greater than 0 for this. The enthalpy is greater than 0. So what's that supposed to mean? Well, let's go through the question which has been given for us here. Now, the question here is that initially at the start, okay, at the start of the experiment, some X moles of carbon monoxide and 8 moles of hydrogen gas are passed, or rather placed in a container with a volume of 10 cubic what? Decimeter. Okay, so initially, carbon monoxide and hydrogen are mixed, and the number of moles of carbon monoxide is 8. The number of moles of hydrogen is what? Is rather the number of moles of carbon monoxide is X. It's given here. The number of moles of what? Carbon monoxide is X initially, and the number of moles of hydrogen is what? Is 8. So they are placed in a container really, really small with a volume of what? With a volume of 10 cubic decimeter. Then later, they are heated to a temperature of what? Of 300 degrees Celsius, so that methanol is produced. Well, from these statements only, we can already generate a lot of information. But let's first read it up to the end. They're then saying, when equilibrium is established, the concentration, okay, the concentration of hydrogen in the container is 0.225 mole per cubic decimeter. And the value of the equilibrium constant is what? 6.22. The first question is, define the term chemical equilibrium. So would someone take that up? Would you like to define that out, chemical equilibrium? Do you still remember the concept of chemical equilibrium? Just a suggestion. You know, we have got to discuss this. Say something. I mean, it's a better way for you to remember the things that you have read over some time. So you want to remind yourself. So just say it out, what you think chemical equilibrium is. Okay. All right, so you could be thinking about it. I'm going to show you something small, just an illustration here on the board to show you something about this thing we are talking about. When we talk of chemical equilibrium, there is something we want to include in our discussion. So just right away here, magnify it. All right, so there we go. Just make it much bigger. Yeah, so now I hope you can see what I'm sharing with you on the screen. Okay, and here we have it. So they're saying equilibrium condition of reaction A to B. Now, one thing you notice here is that 3 moles of A is going to B and 3 moles of B is going to A. You get what that means is each time reactant A, okay, each time reactant A is losing up to 3 moles of what it had, it will be receiving 3 moles of what it is missing. You see that? So it's like, well, you lose, you gain, you lose. So as you are losing, you're also gaining. You know, it's like you're at the Forex and, you know, you're giving your currency rand and you're getting another currency dollars. So you give this, you take the other one. Basically, much as it appears like there is some exchange of something or there is a loss of something, but immediately there is a gain of something. This is called dynamic equilibrium. Okay, it's called dynamic equilibrium. Some type of equilibrium which is attained when there is some type of exchange of something. Now, the next thing is, well, let's see the next picture right here. This is also what we are dealing with. Now, when you look at this flask A and flask B, you notice that at the start, flask A is having a lot of the molecules, okay, evaporating, very much like escaping. And obviously, with that escape comes what? Comes decrease in volume. But because they notice, or because there is no escape route here, I mean, initially, they are jumping out of the main block, the main body, the main liquid, and they would like to escape as vapors up here. But because the cylinder is sealed, because the flask is sealed, they can't reach there, and eventually they will fall down. And time will come when the rate at which these molecules are escaping as vapors will be equal to the rate at which they are condensing, they are changing into what? Into water. That rate, that point when the rate at which the evaporation equals the condensation is what we call equilibrium, okay? And yeah, also here we have got the description. It has come quite clearly. Thanks for this. It reads, when equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance, you know. Now, this is a good suggestion, but this is the answer to another question. It's still a correct answer, but to another question, okay? It's for the other question, which is question what? Which is question 6.2, which is asking for Le Chatelier's principle. So you have given us the Le Chatelier's principle. And you see, you guys, this is what I say. It's always good to suggest something, because then if you have got it right, it will reinforce, it will really improve, it will make you remember it nice, it will get stuck the right way. And if for some reason you have missed the point of your, or like the way it has given here, you have given a correct answer to another question instead, then it is easy for you now to connect this answer to the other question, because now it will be clear that, well, this is not the right answer for this question, but it's the right answer for the other question. So the suggestion coming from one member is what is called Le Chatelier's principle. And it's a question that we have here. It's question what? It's question 6.2. In 6.2, we are required to state Le Chatelier's principle, and this max is going right away to this what? To this answer. It's already been given. So you see, we are still struggling there with the definition of what? With the definition of chemical equilibrium. So yes, you could write your own. I mean, this is solution to 6.2. You can still suggest, let's say please go ahead and say something, or you can type what you think chemical equilibrium is. For 6.2, we have already got the solution. When we reach to it, you know, it will just be that we will have just to stick with this. While I continue to illustrate for you the what? The concept of equilibrium or dynamic equilibrium using pictures, okay? So the next picture after this other one here is a picture which comes from a very much practical thing that we basically meet every day. Think about this. You possibly have not thought of it, but think about getting onto an elevator, okay? Think about getting onto an elevator. Then, you know, the elevator is coming down, okay? The elevator, rather, the elevator or escalator, if you like it. So the escalator is moving down and you're moving up. Don't you think that could be a good way to jog around? You know, the escalator is moving down, really trying to move down, and you're moving up the same speed with which the escalator is moving. Yeah, that is called dynamic equilibrium, okay? That is called dynamic equilibrium. Dynamic equilibrium means the exchange rate is the same. The rate at which you are moving forward, like in the case of this girl, equals the rate at which the escalator or the elevator is what? Is moving down. So in a very precise way, we could say chemical equilibrium by definition is a dynamic equilibrium, okay? It's a dynamic equilibrium when the rate of forward reaction equals the rate of reverse reaction. So now instead of talking about movement or exchange or what, here we are talking in terms of reaction. So we say chemical equilibrium is a dynamic equilibrium, okay? It's a dynamic equilibrium when the rate of forward reaction equals to the rate of reverse reaction. Okay, that is how we do what? We define chemical equilibrium. Now, I can go ahead and write it down. Let me just write this down so that in case you're noting it, it will be easy for you. So that is 6.1. Where we say chemical equilibrium is a what? It's a dynamic equilibrium. Dynamic itself means some type of exchange, some type of movement, okay? Dynamic, it's the exact opposite of stationary, okay? Stationary means no movement, no exchange, nothing. Dynamic means exchange, movement, something. So it's a dynamic equilibrium when the rate of forward reaction equals the rate of or equals to the rate of reverse reaction. So it's very much like saying if the forward reaction is about producing something, okay, like the way I've illustrated for you here, if the forward reaction is about producing something, like in this case, production of vapor, okay? So if the forward reaction is about production of vapor, then the reverse reaction is the what? Is the opposite of production of vapor, which is production of water in this case, which we say, or we call it condensation. So the rate of condensation equals the rate of evaporation, or the rate of evaporation equals the rate of condensation. The rate of forward reaction equals the rate of reverse reaction, okay? Obviously, evaporation is still happening. Well, evaporation is still continuing, but also condensation is what is continuing. So for example, if 5 moles or 5 molecules evaporate, then 5 immediately condense. That is what it means. The number evaporating equals to the number condensing. That gives us the definition of chemical equilibrium. Well, let's move to the next question, which is what? 6.2. So 6.2 is asking us to do what? To determine the initial amount, or the initial number of moles, which is given as X in this case, of carbon monoxide that was placed in the what? In the container. Well, this is up to some 9 marks. So you see, we have got to do this with a lot of care. Now, what I'm going to do is to extract. We will be talking about carbon, or we could use a table. We could use a table instead. Let's sketch a table, and we see what we can do with a table, so that it's much more organized for us. So here I'm going to have a table, and we write everything inside the table. Well, how many things do we need in the table? Just put this, all right. Yeah, like that. Okay. So what are we going to have in our table? We are going to have these 3 things that we have talked about. And what are they? The carbon monoxide, it's given here. We are mixing things. We are mixing carbon monoxide with the hydrogen, so that we get what? So that we get methanol. So we'll be having a space for carbon monoxide and hydrogen, and later what? And later methanol. So let's have them written here. So we'll be having here CO, then we'll be having here hydrogen, then after that we'll be having what? Let's put this, okay. Then we'll be having methanol, okay. Be having methanol. Oh, just wanted to put some a subscript, yeah. Let's deal with it like this. The subscript will come right here. All right, so there we go. Now, what do we have here? Well, here we will have the initial number of moles. Let's call it the initial number of moles. The initial number of moles. Then, when we are done with the initial number of moles, we will now look at the what? The number of moles used. Because the whole thing is we are mixing this carbon monoxide with what? With hydrogen. So initially, that is what we have. Then now, as the two begins to react, as the temperature is increased again and again and again in the presence of a catalyst, we will then have what? These two forming that, meaning we will now be talking about the number of moles used, okay? So we'll be talking about moles used. And you see the moles, the number of moles of carbon monoxide and the number of moles of hydrogen used is what will give us the number of moles of what? Of methanol, which is formed here. So we'll also be talking about the number of moles. If it is not used, then it is formed. All right, number of moles formed. Like that. I would like to extend this one a little bit so that these things stick to one line. Yes, like that. And this, and yeah, this way. Then we will also talk about moles at equilibrium, okay? We'll have to include moles at equilibrium. Yeah. Okay, moles at equilibrium. And then finally we'll be having what? We'll be having the concentration right here. So let's say the concentration here, we can now put the formula right away. Be like concentration C will be calculated if it's not given, okay, from this formula here. And what's the formula? Formula is the number of moles per unit volume. Yes, that's what we have. Okay, so now let's extract this thing and we see what we can get from it. So the number of moles of carbon monoxide initially was given, and what was it? The number of moles given initially is X. X is the number of moles of carbon monoxide initially. So we put it right here in our table and we call it X, right there. Then the number of moles of hydrogen initially 8. So those were the two available. At the start, there was nothing for what? For methanol. Then now, how about the number of moles now used or formed? That is now where the calculation bit comes in. We now have to get back to the question and we read and we see the type of information we can extract. Okay? All right, so how are we going to deal with this? Well, the thing we are having here is this, that initially, okay, initially, the number of moles is given here of hydrogen and carbon monoxide. But also they have given us the volume here. And since we have this piece of information, we can calculate, okay? We can calculate the number of moles of hydrogen that was used, okay? So how do we get this? Well, let's first get everything extracted. We start with the number of moles. Right here. This is what we are looking for, the number of moles of this one used and this one also. So about hydrogen, what do we know? Well, the thing we know about hydrogen is that at equilibrium, as it was written here, just read again. Okay, they said when equilibrium is established, the concentration of hydrogen in the container is 0.225. So we now have the concentration, okay? And also we have the volume. So let's put it down. The concentration for hydrogen, we say concentration C, okay? Concentration C is given as 0.225. That's what we have been given. What else do we know? Well, the other thing we know is also at equilibrium. No, the volume did not change. It was just the temperature that was being increased, okay? So there we go. Here, the volume is 10, like that. Can we calculate the number of moles? Yes, we can calculate the number of moles. Now, the number of moles we are calculating right now is the number of moles of hydrogen that was used during the what? During the process of formation of methanol. So what is going to be the number of moles here? Well, we will use the formula which is given right up here. And the formula is what? Concentration equals to number of moles per unit volume. And since we are looking for number of moles N, we are going to multiply the concentration C times the volume V. And so this way we will get what? We will get N equals C times V. That is CV, if you like it. And so when we substitute that, what is the value of N going to be? Well, the value of N, let's scroll down a little bit. The value of N going to be C, the concentration, which is 0,225 times, okay? Times the number of mole, which is rather times the volume, which is 10. What do we get from here? We get 2,25. That's what we get? Yes. Just moving this one place of decimal to the right to this point. So that's 2,25. Now, after getting the number of moles, well, we can come and put it right down here, okay? So we put this as 2,25. That's what we have got, the number of moles right here. Yes, this is the number of moles that we have got so far. Wait. Now, notice that after calculating the number of moles here, unfortunately, we have not yet copied the formula. Let's first get back to this. Now, we have calculated the number of moles that have been what? That basically the number of moles at equilibrium. What we had initially is that the number of moles of hydrogen was 8, but now at equilibrium, the number of moles is 2,25. So the question here is, how about the number of moles? It's like trying to say, well, you went to buy something. You had, for example, 500 with you, okay? So now, after having 500, okay, after going to a shopping mall, you notice, well, what is remaining with you is only 100. So how much money have you used? The amount of money you have used is 500, which is the initial amount of money, minus the amount of money, okay, which is remaining. You see that? That is what we are talking about. So now to write the number of moles here, this is going to be the number of moles that we had initially, 8, minus what? Minus the number of moles which is available right now. And what is that? That is 2,25. Okay, that is how we are bringing this thing here. You see? So to find the number of moles used, or to find the amount of money you have used, you now have to see what you have right now minus what you were having before. And that gives us what? That gives us 8 minus 2,25. You guys have a calculator with you there? I've got to use my own. Yeah, do something, do the calculation. Please put that value, subtract 2,25.8 and see what we get. Okay, so I'm using my calculator right here. You guys seem to have placed your calculator a little bit far from you. So what is this going to be? Well, this is going to be 8 minus 2,25. That gives me what? What I'm being given here is 5,75. So this is what we have here. 5,75. All right. So any question up to that point? What we basically did is we used the information. Oh, all right. Someone had already given us here. Yes, it's 5,75. Thanks for that. Let's go. Now, the next thing we are moving to is this. Now, when you look at what we have here in the original expression, the formula is that carbon monoxide is mixing with what? With hydrogen, so that methanol is formed. The thing we want to look at here is the what? Is what we call the mole ratio. It's like trying to say, for every 1 mole of carbon monoxide, there are 2 moles of hydrogen. Now, this is what we have at equilibrium, okay? You guys listen carefully. This is what we have at equilibrium. For every 1 mole of carbon monoxide, what do we have? We have 2 moles of hydrogen, and that will generate 1 mole of methanol. Since we already have the number of moles, okay? Since we already have the number of moles that was used, and the mole ratio is 1 to 2, what would be the number of moles of carbon monoxide? Okay? What would be the number of moles? We want to find out what we are going to write here. So you guys, what do you think? What do you think will be the number of moles of carbon monoxide that has been used? Because for every 2 moles of hydrogen, there is 1 mole of carbon monoxide. Or it's like trying to say, for every 1 mole of carbon monoxide, it's like if you have, you guys get this description. If you have some young brother or, like an elder brother or someone like that, each time they give them something, you're also given something. You notice that? Now, if this is the ratio, each time you are given 1, they are given 2. But this time, they have been given 4. Well, how many have you got? You will have got 2. If they give them 6, how many will you be having? 3. If they give them 10, how many will you be having? 5. You always get half, okay? So now that means we have to divide what? We have to divide 5,75 by what? By 2. That is S of the mole ratio. And what do we have here? Well, we'll be having 2, what? 875. That's what we got. Now, the next thing here is this. How about the number of moles here? We still look at the same what? Mole ratio. So here we have 1, 2, 1. So we'll still be having the same number here, which is what? 2,875. Yes, that's what we have got so far. Now, any question on that? If you do have a question, then you have got to be willing to do what? You have got to be willing to write it and just send it right over here. The next thing we now want to look at is the what? The moles at equilibrium. Okay, well, the moles at equilibrium, we already calculated that. The moles at equilibrium, we had already calculated. The mole at equilibrium for hydrogen, we already calculated. We just write it there. So let's put, what is the value? The value is right down here, 2, what? 2,25. So this is the what? The mole of hydrogen at equilibrium. Just put it right there, 2,25. Now, notice that the interesting thing here is that the number of moles, just put this here. So notice that the number of moles generated or formed here won't change. So we will still be having what? 2,875. Okay. Now the thing we are dealing with, how about the number of moles of carbon monoxide? The number of moles at equilibrium, okay? The number of moles at equilibrium of carbon monoxide is going to be the number of moles. It's still the same thing. It's not like the same 2.87, but it's the same illustration as I was indicating. You went to the shopping mall, you had some money with you, and you noticed that this amount of money, okay, has been used. So what is that supposed to mean? Well, at that point in time, what you are remaining with, or the mole at equilibrium at that point of time, is going to be what you had at first, which is this one, minus what was used. That is what is remaining with you. So you bought a lot of stuff, you know. Much as when it comes to the things of money, it's a lot easier to count the money instead of going through the tail slip and being like, well, I had, you know, 500, and now let me see, I have bought this, checking through from the tail slip. You know, it won't work nice. So you would like just to do what? To count. But here, it's not going to be easy for us to count. So we just write it as x minus 2, 8, 7, 5. Yes, that's what we have got so far. All right. Now comes the what? Comes the concentration. Okay. So how about the concentration thing? Well, the concentration, we have been given the concentration of hydrogen was already given for us, right? Yeah, it's what we used here. The concentration of hydrogen was already given. So what do? We just write it down here, and that is what? 0,225, like that. How about the concentration here? Well, the concentration here, it's going to be, we now use this formula, number of moles per unit what? Per unit volume. This is the number of moles. What is the volume? They're in the same container, so the volume will not change. So what are we going to have? We are going to be having x minus what? 2,875. That is the number of moles. Now we have to divide it by what? We have to divide it by the volume. And what's the volume? The volume is 10. They're in the same container, so the volume remains the same, okay? Yeah, so now, well, from that, what do we have here? We also deal with the same thing. It's going to be the number of moles divided by, let's write it here, S2, 875. So this is the number of moles, okay, at equilibrium. Now we have to divide it by what? We have to divide it by the volume, which is 10. When we do that, what do we get? Well, let me check with my calculator here. So this is 2,875 that we have to divide by 10. Yeah, I get 0,287. So instead of writing this calculation thing, we just write the actual value. We don't need now to put this. This is going to be 0,2875. Yeah, that's what we have got. Okay, so now here is the question. How do we find the value of x? Now notice there is one piece of information we have not yet used. Okay. All right. Yes, there is a question here. There is a question. Maybe before we move forward, I had not seen the question. The question is, how did we find, okay? How did we get the number of moles used for carbon monoxide? How did we get the number of moles used for carbon monoxide, which is this one here? That is the question we're dealing with right now. Now, what we did, the first thing we did, okay? The first thing we did was to find the number of moles of hydrogen used. That is the first thing that we did. Now, we did that one by multiplying the concentration of the hydrogen by the volume, and we got 2,25, okay? That is what we got for the number of moles. Now, to find the number of moles of carbon monoxide, what we did was to compare the mole ratio. We normally like to put it as a rough work. So let me put it here. I would like to call this now carbon monoxide. Carbon monoxide, like that. So the mole ratio is that for every 1 mole, we could put like this. For every 1 mole of carbon monoxide, there are 2 moles of what? of hydrogen. You see that? So the ratio is like this. The ratio is 1 to 2 to 2. Okay? The ratio is 1 to 2. Now, the next thing we have is we don't know the number of moles of carbon monoxide, but we know the number of moles. Let me put this is lowercase n like that. But we know the number of moles of what? Of hydrogen. And what is that? The number of moles of hydrogen is 2,25. You see, that is what we have. So the question now is, how do we find the value of n? How do we find the value of n? You see that? Now, mathematically, this 1 to 2 can be written as 1 divided by 2. Okay, mathematically, we can write it as 1 divided by 2. So let me write it like that. 1 divided by 2. Then if we equate it to this other one here, which is n divided by 2. N divided by 2. Notice that this n we are using now is simply for the sake of carbon monoxide. It's not the same as this other n which is up there. So this is 2,25. Okay. So once again, after finding the number of moles of hydrogen, to find the number of moles of carbon dioxide, we use the method of mole ratio, or we use the concept of mole ratio, which means for every 1 mole, because it's given here, it's given for us here. You see, it's like there is a silent, let me put here 1, so that is easy for you to see. There is 1 there, and also there is 1 here, like that. So for every 1 mole, this one here, of carbon monoxide, there are what? There are 2 moles of what? Of hydrogen gas. That's the reason we are having here 1 to 2. But now, for this other part which we are doing, which has got us this one here, we now don't know the number of moles of carbon dioxide, but we know the number of moles of what? But we know the number of moles of hydrogen. So if we do that, okay, but we know the number of moles of hydrogen. So if we do that, have I put? No, this is supposed to be the other value, which is 5,75. Sorry for that. Yeah. So this is what we have. Okay. So for every 1 mole of carbon monoxide, there are 2 moles of hydrogen. Now, if we are having this number of moles, this is 5,75. If we have this as the number of moles, then now can we find the value of n? Yes, we can find the value of n. What we do at this point is we just cross multiply. So when we cross multiply, we'll be having what? 2 times n equals to 1 times the other quantity. And what will that be? Well, 2 times n is going to be 2n. And what we are going to be having the other side is 1 times 5,75, which is what? Which is 5,75 times 1. It stays like that. So now to find the value of n, okay, to find the value of n, which in this case is the number of moles of what? Is the number of moles of carbon monoxide. We divide 5,75 divided by 2. And when we do that, we now use our calculator for that. And that should give us a value of what? A value of n, which is equals to, well, we calculated that and it gave us 0 equals to 2,875. Is it 875? Yeah, it's 875. Yeah. So this is how we calculated it. So this is how we got the number of moles of what? This is how we got the number of moles of carbon monoxide used. Now you might wonder why we have put this one, okay? Why we have put this instead of 2, this one here. Why have we put 5,75 instead of this? Well, what we have calculated here, this one here, is the number of moles of hydrogen at equilibrium. But they said the number of moles of hydrogen initially is 8. You see? So if initially we had 8, and right now we have 2.25 or 2.25, the question is, how much have we used? To find what we have used, we have to look at what we had initially, then from it, we take away what we have right now. So you went to buy some things from a shopping mall, this time with 300, and right now you're having only 20. How much have you used? What you have used is going to be 300 minus 20, which is going to give us what you have used. So in the same way, the number of moles initially was 8. And the number of moles that we have right now at equilibrium is what? Is 2.25. So the number of moles that was used is this one here. Then after finding the number of moles that was used, we now use the mole ratio. The mole ratio is that for every 1 mole of carbon monoxide, there are 2 moles of hydrogen. So the question here is, if that is the ratio, then what if there are up to 5.75 moles of hydrogen? What are we going to have for what? For the number of moles of carbon monoxide. That is when this small mathematics will be introduced, because 1 to 2 can be written as 1 divided by 2. The ratio does not change. And so we do what? We now equate it to n divided by this other one. And from it, when we cross multiply, we get 2n equals to what? 2n equals to 5.75. When we divide both sides by 2, we get 5.75 divided by 2, which gives us 2.875. That is how we have calculated the number of moles of what? The number of moles of hydrogen, rather the number of moles of carbon monoxide, which is here. The other question would have been, how did we find this? How did we get 2.87? The mole ratio is also the same, okay? The mole ratio is the same. The mole ratio of hydrogen to methanol is also the same. It's like saying for every 2 moles of hydrogen, there is what? There is 1 mole of methanol. So if you like it, we could check that also real quick. So we say methanol here. Like that. So the mole ratio is that for every 2 moles of hydrogen, there is 1 mole of what? Of methanol. How did we get the 1? It's given here. You see, it's given in the original equation. Here there is 1, here there is 2, and here there is 1. We are done with these 2. Now we are dealing with this last 2. So here we have 2, here we have 1. So for every 2 moles of hydrogen, there is what? There is 1 mole of carbon, rather methanol. So the mole ratio is like, well, each time one quantity is doubled, the other one is what? Divided by 2 or halved. So now, if we are having this ratio, and now in this case, 2 is 4. So now we are looking for, like this, we are now looking for the number of moles of methanol. Let's call it N. What do we have here? We have 5.75. You see? So the question is, can we find the value of N? Yes, we can find the value of N. We can find the value of N. We use the same relationship. And what is the relationship? The relationship is that 2 to N, rather 2 to 1, can be written as 2 divided by 1. So we'll write this as 2 divided by 1. And we make it equals to what? We make it equals to 5.75 divided by N. 5.75, which we do what? We divide by N. Like that. So in the next step, we do what? We cross multiply. So when we cross multiply, what we get is 2 which is right here, we'll multiply what? N, so that we get 2N. Then this one will multiply the other one, 5,75, so that we get what? We get 5,75. So now the next thing is to find the value of N. How do you find the value of N? We can find the value of N when we divide 5,75 by what? When we divide 5,75 by 2. Like that. And so when we do that, what we get is the value of N. N in this case is the number of moles of methanol, which is what? The same value as what we had got initially, 2,875. Now, that is how we have got what we have in the table here, which is this one. Then after that, well, at equilibrium, this is what we have. Okay? At equilibrium, this is what we have. The number of moles of methanol does not change, stays the same. Okay? Then what are we dealing with now? This one here is the value that we have. Okay? So it's like, well, initially we had X. This is what was used. So what do we have now? We have X minus what was used. That is what we have right now, which is what? At equilibrium. So using this relationship here, C equals to N divided by V, we can write this for carbon monoxide and this one here for methanol. We also get this one for methanol after dividing this quantity here by 10, 10 representing the volume. So the formula is number of moles divided by volume. The number of moles is given here, divided by 10, so that we get what? 0,285. And up to that point, this is what we have. Yes, any questions so far? Any question?
Sir, may you please re-explain this part that you just did now?
The part where, okay, all right. So fine.
Yes, please.
All right. So there we go. Now I'm going to get to the moles again a little bit, then we move on to this. So let me get to this. So now here is the thing. We calculated the number of moles formed. The initial question was, how did we get this? I explained it. Now, the moles at equilibrium, this one was given, okay? This one was given already. It was given in the question. Let me make it bold like that. So that one was given. The number of moles at equilibrium for carbon monoxide is going to be, it's like we are dealing with right now. You had some money, you bought something, or you had something, you gave others away. So what do you have now? What you have right now is what you had initially minus what you have given away. What we had initially for carbon monoxide is X. What we have given away, what was used was this. So what do we have now? We have what was having initially minus what was given out. That is how we got this. This one was given. Also, this one isn't changing. The next thing we are dealing with is this one here, the concentration, okay? Now, the concentration is calculated. When we know the number of moles, then we divide it by the what? By the volume. Now, this whole setup is kept in a small container of a volume of 10 cubic decimeter. So now, how do we calculate the concentration of carbon monoxide? The concentration, rather not the, the concentration. So the concentration of carbon monoxide is going to be the number of moles of carbon monoxide at equilibrium divided by the volume, which is 10. And that is what we have. We cannot simplify this and write a definite value because we don't know the value of X. The other thing here is this. The number of the concentration of hydrogen is going to be the number of moles of hydrogen, which is what? 2,25. Then we divide it by 10. They are in the same container, so the volume does not change. It's also 10. So we'll be having 2,25. If we divide by 10, what do we get? We get 0,225. Then, to find the concentration of methanol, we also have to know the what? The number of moles. Then we divide it by 10. So when we divide this number of moles by 10, what we get is 0,287. So that is how we get the concentration of this one here, carbon monoxide, the other one, hydrogen, and methanol. That is for the concentration. Now, after getting the concentration, okay, I hope you've got that. After getting the concentration, the next thing we want to look at is, how do we then find the value of X? Because that has been the question all along. How do we find the value of X? Well, to find the value of X, there is one more thing we need to do. We need to find the what? We need to find the concentration of carbon monoxide. There is one piece of information we have not yet used, and that piece of information is right here. Check this. We did not use 6,22. And what is 6,22? 6,22 is the equilibrium constant. And so let's use it right now. So the equilibrium constant K, sometimes written as K's. All right, let's put it here. The concept of equilibrium constant. Like that. So we say the equilibrium constant K can be calculated when we know the concentration of what? Of the products. And then we divide what we know by the concentration of what? Of the reactants. Like that. So if we have like 2 or 3 reactants like that, then you know we keep doing stuff like that. So what do we have here? Well, what is the concentration of the product? Do we have the concentration of the product at equilibrium? Well, we do. It has been given to us, but let's first write the formula. The formula here is the product. The product is methanol. So let's put it right there. Methanol is CH or H with 3 here. Okay, with the 3 there. Now notice we have to raise this to what? We have to raise this to the number of moles. So when we raise it to the number of moles, what do we get? Well, oh, sorry, just trying to write this. Yeah, so we have to raise this to the number of mole. The number of mole of methanol is 1. Then now, what are the products? There are 2. There is carbon monoxide, CO. Okay, we have carbon monoxide, CO. What else do we have? We also have hydrogen, which is what? Which is H2. So this is the formula. H2, write it down here, like that. So now the next thing is, we have to raise this to the number of moles. And also we have to raise this to the number of moles. So what's the number of moles of carbon monoxide? The number of moles of carbon monoxide is 1. The number of moles of hydrogen at equilibrium is 2. So at this point, we can then go ahead to substitute. We have now generated the formula. So in substitution, we therefore say, K, which is the equilibrium constant, given as 6,22, is equals to what? The concentration of methanol at equilibrium. Do we have that? Let's check the concentration of methanol at equilibrium. Yes, we do. It's right here, okay? So this is the value of the concentration, 0,2875. Just put it down here. Yes, that's the concentration of what? That's the concentration of methanol. Now, this concentration of methanol, we have to divide it by the concentration of carbon monoxide. So let's see, what do we have for the concentration of carbon monoxide? We see from the table. All right, we don't have it. So let's keep it as CO. Yeah, we just keep it like that. This is CO. Then do we have the concentration of hydrogen at equilibrium? Let's see. The concentration of hydrogen at equilibrium, we do. The concentration is right here, 0.225. So we just substitute that one right away. 0.225, that is times. Then notice that we have to put it in a bracket, okay? So this is 0.225. But remember, we are squaring it. So we raise it to what? We raise it to 2. Like that. So from here, we can find the concentration of what? We can find the concentration of carbon monoxide. The only thing remaining here is the use of the calculator. I would like to encourage you guys to do this. Find for me the concentration. Just use your calculator. Me, I'm going to be doing the typing work here. Then type and send it to me. Type that. Find for me the concentration. Okay, find the concentration and just write it to me. The easiest way to find the concentration is to do this, is to take CO that side and bring 6.22 down here. That is how you find the what? The concentration. It's what we call cross multiplying. You know, it's called cross multiplying. Cross multiplying, you transfer CO, take it there. Then you know, get this 6.2 to bring it down here. Instead of taking the whole of this one there, then later dividing, no, just take only CO that side and bring this one down here. Then tell me what you have got. Okay. I guess that should not be very difficult. What I said is you will have 0.2875, which you will divide by 6. Okay, you divide by what? Well, 6.8, no, to 2. This one here, you again multiply by what? 0.225, which you have to square. Okay. So, yes, I'm going to wait for your answer, guys. For this one here, I'm going to wait for it. I'm giving you up to about a minute to find the concentration. Cross multiply and do that. And write for me the answer in the chat. Yeah, just put your calculator next to you. Yes, what have you got? I'm going to wait for this value. Let me be waiting while I type this value that you have got. Okay, just put it for me in the chat box. This value that you have got is going to be equated to what? To this one that we had calculated. This is 0, comma. Is it 0, comma? No, it's 2,875. Use the calculator of your phone, guys. Should not be difficult to do that. Use the calculator of your phone. You see the value you have got is what we now have to equate to that. So tell me what you have got. Oh yes, I've got one direct message here. The direct message is giving us a value for the concentration. It's giving us a value for the concentration, which I'm just going to copy. It is 0, comma what? 0, comma 9, 1, 3, 0, 2. Yeah, that is what I have been sent. So that's what we put here. 0, comma 9, 1, 3, 0, 2. Yeah, so from here we can find the value of x. The only thing is we just cross multiply, okay? So cross multiplying means, well, it's a lot easier to see it when we put this one over 1. So let's just put this over 1. Okay, let's put it over 1 like that. So if we put it over 1, the next thing we are going to be dealing with is we have to multiply 10 by that. Then later we take this one the other side, okay? So we are going to be having x minus 2, 875 now equals to 10 times that value, which is going to be 9, what? 9, 1, 3, 0, 2. So to find the value of x, well, to find the value of x, we now have to transfer to the other side, these two. So what is it going to be? It's going to be 9 plus 9, 1302 plus 2, so let me use my calculator for this now. 9, 1302 1302 added to 2, 875. That's going to give me a value of 12,0052, which we can leave it at 12. All right, maybe just put this. Then we conclude and say, that x, just put it down here, x equals to what? 12. We can conclude. So what's the value of x? Well, that's the number of moles initially. So just a quick recap on what we did for this last part is this. We completed the table. After completing the table, we needed to find the value of x. So how would we find the value of x? Well, one way of finding the value of x is to use the other piece of information which is given about the equilibrium constant. The information given here is that the equilibrium constant K equals 6,22. And now what we know is the equilibrium constant equals to the ratio of the concentration of the products to the concentration of the what? Of the reactants. Mathematically, this is how we write it, okay? We say the equilibrium constant K equals to the concentration of the products right here divided by the concentration of the what? The reactants, with their moles raising or being raised as the what? The exponents. And so the equilibrium constant K was given. Now we substitute it here. The concentration of methanol, the product, we calculated it as this. The concentration of carbon monoxide, we don't know, so we write this, okay? Then after that, we multiply with the concentration of hydrogen, which we calculated as this, but we have to square it as of the what of the formula. So how do we then get the concentration of carbon monoxide? Well, we just cross multiply, okay? Well, is this so confusing? I guess it's not, but if it is confusing, you just inbox me and I again explain it as a rough work. Otherwise, what I said here is to find the concentration of carbon monoxide. What you do is you cross multiply. Now, cross multiplying in this case would require us to multiply what? The whole of this denominator, by what? By 6,22. We would have to multiply this by that, then this numerator here by 1. Then later, we would have to divide this and that, both sides. In other words, just to make it quick, we crossed multiplied with only what? CO. So we took CO, that side, left-hand side, and we brought 6,22 down here. But mathematics could be confusing. I'm going to do this again right down here so that you guys can see it nicely. So when we cross multiply on one side, we are going to be having 6,22 times, okay? Let me put it, times the concentration of carbon monoxide, put there CO, times what? Times the square of this. Let's just write the square right away. You know, this is going to disturb us putting subscripts. So it's 0,225 squared. It's giving us 0,050625. That is what we have got. So that is what we have on one side. Then on the other side of the equal sign, what are we going to have? On the other side of the equal sign, we have this value here, which is 0,2875. What are we looking for? We are looking for the concentration of carbon monoxide. How do we get it? Well, to get the concentration of carbon monoxide, we first do what? Let's write it here, CO. We multiply this one, 6,22. By what? By 0, we multiply this by 0,050625. Okay, this is what we have got. Now, when we multiply the two, what do we get? Well, according to my calculator here, we are going to get input times 0,3148875. That's what we get. Equals to what? 0,2875. That's what we get. So can we find CO? Yes, we can find the concentration of carbon monoxide. And how do we get it? The concentration of carbon monoxide in this case is going to be this value which we have got on the right hand side, this quantity here, divided by the other one. You see? So let's divide it. So we are going to divide this. To 875. Just write this thing. 0,2875 divided by 0,3148875. Okay, so with my calculator here, I'm getting 0,91302. plus some other values, like 4, 4, 9, 2, 8, 7. Those are the other values. It's not very necessary to have all these other ones. We just reduce it to that value. So after finding the concentration of carbon monoxide, okay? After finding the concentration of carbon monoxide, as this value here, we now equate it to what we had on the table, because initially we had calculated from the table that the concentration of carbon monoxide is this. You see, this is the concentration of carbon monoxide at equilibrium. So what we do here is we now make that concentration equals to what we have got, which is here. This is now where the calculation is. So this is what we do. So the concentration of carbon monoxide at equilibrium is now equated to this, which we have got. And then we cross multiply and later get the value of X. This is how we find the value of X. Any question, guys? Any question? Are you guys still following? All right, so if there is no question, then we just conclude with the set with the 6.2. The remaining question is 6.2 and the extension of the graph and stuff like that. That is now a small part. So what is it remaining here? Well, what they're saying is the reaction rate versus time graph below shows the what? How the equilibrium is reached. And the dotted line indicates the reverse reaction, okay? The dotted line indicates the reverse reaction. It's like the rate at which something is being produced, you see? This is the rate of production. This is the rate of reverse production. This is how it's happening. So we are supposed to state Le Chatelier's principle. Well, Le Chatelier's principle was already stated, okay? It was already stated. And what was it? Well, it was stated by one member that just get it for you in her own words. Yeah, right here. It was stated that when equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose disturbance. Yes, I'm seeing here, is any question? Is anyone having a question? If there is no question, then, we are moving to 2.6.2, which is about equilibrium. No, not equilibrium constant. It's about Le Chatelier's principle. It was already given. We had already seen it. When equilibrium in a closed system. Remember, it's very important. The equilibrium is in a closed system, okay? So when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium. How? By reinstating another equilibrium. This case, by favoring the reaction that will oppose the disturbance. Oh yeah, so there is one question here. That does it matter when you don't use X? Does it matter when you don't use X as a variable to get the initial mole and you use a different method? Okay, if you use a different method, it's fine. We have discussed only one method. There are like possibly 4 different methods you can use to find the value of X, which is given in the question, okay? So X was given in the question. If you're going to use some other value, well, it's still fine, but you will have to conclude that X equals to that value you have got, okay? It's fine, you can use some other value and you can use a different method, it's okay. There is no problem using another method. The memo will always be having many different methods. And if another learner has come with even a different method from that other one, which is already on the memo, it's still reviewed. If it's correct, it's still awarded marks. So there is no problem sticking to one method. One method may be so long, or one method may be difficult for you to understand. So you have to stick to what is easy for you to understand, okay? You have to stick to what is easy for you to understand. You use the method that you understand. And we are supposed to redraw the graph. Now, the program I'm using is not so good at drawing graph. It can only draw a table. So I'm just going to show you the graph, which is already drawn, which will show how reaction rate will change with time if a catalyst is added and temperature is increased, like from the value which is there, 300, to some other value. So this is how our graph will appear. This is how the graph will appear. This is the graph. So I guess you can see the graph, that is 6.3. We are supposed to do what? We are supposed to illustrate it. So when you increase the catalyst, immediately the reaction rate will increase. And what do you see? You see this one up here. From that time when it was increased up to some other time, because again, the equilibrium have got to be restored, okay? The thing here is you increase the catalyst. When you increase the catalyst, you know, things will change. The rate of reaction, the rate of production of methanol will increase. And because of that, that means equilibrium have been what? Disturbed. So the system will have to reinstate a new equilibrium. And that new equilibrium, which is reinstated, is to help stabilize. So you increase the rate of production, then the rate of reverse production will also have to be increased so that equilibrium can be achieved. How do you see that? That is for this section here. This section here is where we now have the what? Is where we have the equilibrium restored. Then you again increase temperature. Then you have this section here. You see, that is what happens when you increase temperature. Temperature is now increased in this section. When you increase the temperature, we see an increase in rate of reaction. Disturbance has occurred and rate of reaction has changed. And because of that, what will have to happen is the system will have to reinstate a new equilibrium. When they reinstate a new equilibrium, what do we get? We get this one now happening. You see? So the rate of reaction is now this value here. Okay? That is what we have. So you get your 2 marks awarded for the graph. You just have to know that when you increase the what? When you increase the catalyst, this is what is going to happen. Rate of reaction will increase. And when the rate of reaction increase, the system will have to reinstate a new equilibrium. The first equilibrium was here. This is the first equilibrium. That is what we have. Then now, because you have increased catalyst, that is how it's indicated. Then a new equilibrium to restore. Then you have again increased temperature, we get that. Then a new equilibrium is restored, we get this, you see? So that is what happens. Now, yes, we are done. You guys got any question? Any question? Any question? Anyone with any question? Because we are done. Any question? If there is no question, then I'm going to upload this. You can watch it again when you find some time. And the link, I will also be putting it in the group. So you can check from there in the group, you know, when you feel sober enough, because it was a long discussion. Maybe you got tired and, you know, you are like off completely already. So it's fine. You can again watch this when you are sober enough. then you get to understand. I will also upload a few questions. It's very important that after understanding this, you go through the questions and again try it on your own and you see what you can get, okay? So let me upload it. Otherwise, we are stopping here for now. And we will continue possibly tomorrow. Thanks so much for your time. Enjoy your day.